We've been through a simple example of dimensional analysis based only on spatial dimensions. We talked about how a Cartesian reference frame has three axes, and each of these axes is going to have a fundamental dimension of length. We can also talk about other entities in this system that would have derived dimensions. For example, there could be an area in this space that would end up having dimensions of length squared, and there could be a volume in this space that would end up having dimensions of length cubed. Now, what this does is give us the essential building blocks for really understanding what numbers mean when you try to map them to reality. And that means we can probably come up with a better or more specific definition of a datum. So we started with a more philosophical definition of a datum being some objective piece of information about the organization of reality, but that's very abstract. That really doesn't get us any further in understanding what a number means. So let's put another definition of datum out there in a quantitative measurement context. And the way I like to define a datum is it's an evaluation of a property describing a given entity within a given reference frame. So if that evaluation is a number, it's critical to know what its units are, to know what scale it's measured on, but it's even more critical to understand the dimensionality of the property, because that's what is actually allowing you to map what that number means in the real world. Now, the real world is a complex place, so we probably need a few more fundamental dimensions than just length for a system that's going to work more generally. So there are several more fundamental dimensions to talk about, but there are remarkably few of them compared to the complexity of that reality. First of all, we can talk about a count, and this is sometimes also called a dimensionless fundamental dimension. So some people say this just means it doesn't have dimensions, but other people say, no, things always have dimensions. That dimensionality just happens to be a count. Don't need to get into that argument, but it's out there. So we designate a count with the number 1, and that's because it operates in algebra similar to how the number 1 operates in algebra. And the count is just a number of things, like you could have 10 apples, or you could have half of all of the apples. If you want to talk about a fraction of things, that's also considered a count. Now, just because it's dimensionless, or sometimes considered dimensionless, doesn't mean it doesn't have units. So you could also have 2 moles of molecules. Moles is a unit that tells you something about what 1 means, and Avogadro's number in this case. But just because it's units doesn't mean it has dimensions. That is still a count, even though it has units. Maybe that's an argument for why there really aren't things without dimensions. So one of the useful properties of dimensions is separate you from units, so you don't have to worry about thinking about that. Just because something has a unit like radians is a unit for an angle, it's the ratio of the arc of a circle that gets cut off by a given angle divided by the radius of that circle. Those are both lengths. It's a dimensionless number. If you just look at the units, you may not know that, and you might get confused with your algebra. But again, if you just understand dimensionality, you don't have to think about that. In space, we've talked about length being the fundamental dimension. Just because they're used so much, I went ahead and threw area and volume on here, even though technically those are derived dimensions. I've also shown some examples of units you might be dealing with, like 20 meters or 120 square miles or 80 cubic centimeters for length, area, and volume. But here, it's also important to recognize that the units don't always directly represent the dimensionality. For example, if you're talking about a volume, sometimes the units used are things like gallons or liters or teaspoons or cups. These are all length cubed, dimensionally speaking, but you can't tell that necessarily just by looking at the unit. Again, I think that's why when you're talking about understanding what a number means, it's better to get away from the units. The units are providing the scale. It's better to think about it dimensionally and recognizing the length squared or length cubed, and not be using the units. So we are frequently trying to think about how things change. And one of the ways to quantify change is to understand how things change over time. So time is a really important dimension for a lot of the variables that we use. We might use the variable lowercase t for time. The dimensions for time are a capital T. This really shows the importance of using square brackets because capital T probably would stand for temperature in other contexts, but the square brackets let you know, oh, that's a dimension. It's actually referring to time. There are lots of different units for time. I've got 45 seconds here, but you have days, months, years, lots of units for time. Mass, the variable we typically use for mass is a lowercase m. This is a fundamental dimension that helps us start to get at the concepts of energy, because it takes energy to move masses or to change the momentum of a mass. Dimensionality of mass is just a capital M in square brackets. Again, lots of units for mass. I've got 123 grams as an example of a unit here, but they're kilograms. Mass is a little tricky because some people might think of pounds as mass, and that's actually not entirely invalid. Technically, pounds is a unit of force. However, as long as you're in the same influence of gravity, like if you're always on Earth and you're always talking about the same acceleration of gravity, then mass and force dimensions can sometimes be used interchangeably. And finally, the last one that we might use more frequently is temperature. Again, here's the variable. Capital T is typically used as a variable for temperature, even though capital T unitalicized in square brackets, that's the dimension for time. The dimensions of temperature are typically specified with a capital theta, Greek letter theta, in square brackets. Temperature has lots of different units. You could have Kelvin, you could have degrees. Now, temperature brings up an interesting issue in the gray areas of dimensionality, because temperature can also probably be represented by the fundamental dimensions. But in a lot of cases, people aren't breaking temperature down into those fundamental dimensions with the type of math that they do. So you can argue whether or not temperature is a fundamental dimension or not, but it's still perfectly valid to show derived dimensions as a single variable when it's convenient to do so.